Welcome to Learn Chemistry Together. This video is about atomic orbital, quantum mechanics. By the 1920s, chemists were aware of constitutional isomerism and had developed the structural theory of matter. The electron had been discovered and identified as the source of bonding, and Lewis structures were used to keep track of shared and unshared electrons. However, the understanding of electrons was about to change dramatically. In 1924, French physicist Louis de Broglie suggested that electrons, heretofore considered as particles, also exhibited wave-like properties. In 1926, Erwin Schrödinger, Werner Heisenberg, and Paul Dirac independently proposed a mathematical description of the electron that incorporated its wave-like properties. This new theory, called wave mechanics or quantum mechanics, radically changed the way we viewed the nature of matter and laid the foundation for our current understanding of electrons and bonds. In order to understand the nature of electrons, it is critical to understand a few simple highlights from quantum mechanics. An equation is constructed to describe the total energy of a hydrogen atom, i.e., 1 proton plus 1 electron. This equation, called the wave equation, takes into account the wave-like behavior of an electron that is in the electric field of a proton. The wave equation is then solved to give a series of solutions called wave functions. The Greek symbol psi is used to denote each wave function, psi1, psi2, psi3, etc. Each of these wave functions corresponds to an allowed energy level for the electron. This result is incredibly important because it suggests that an electron, when contained in an atom, can only exist at discrete energy levels, psi1, psi2, psi3, etc. In other words, the energy of the electron is quantized. Each wave function is a function of spatial location. It provides information that allows us to assign a numerical value for each location in three-dimensional space relative to the nucleus. The square of that value, psi2 for any particular location, has a special meaning. It indicates the probability of finding the electron in that location. Therefore, a three-dimensional plot of psi2 will generate an image of an atomic orbital. Electron density and atomic orbitals. An orbital is a region of space that can be occupied by an electron. An occupied orbital must be treated as a cloud of electron density. This region of space is called an atomic orbital, AO, because it is a region of space defined with respect to the nucleus of a single atom. Examples of atomic orbitals are the s, p, d, and f orbitals that were discussed in your general chemistry textbook. Phases of atomic orbitals. Our discussion of electrons and orbitals has been based on the premise that electrons have wave-like properties. As a result, it will be necessary to explore some of the characteristics of simple waves in order to understand some of the characteristics of orbitals. Consider a wave that moves across the surface of a lake. The wave function, psi, mathematically describes the wave, and the value of the wave function is dependent on location. Locations above the average level of the lake have a positive value for psi, indicated in red, and locations below the average level of the lake have a negative value for psi, indicated in blue. Locations where the value of psi is 0 are called nodes. Similarly, orbitals can have regions where the value of psi is positive, negative, or 0. For example, consider a p orbital. Notice that the p orbital has two lobes. The top lobe is a region of space where the values of psi are positive, while the bottom lobe is a region where the values of psi are negative. Between the two lobes is a location where psi equals 0. This location represents a node. Filling atomic orbitals with electrons. The energy of an electron depends on the type of orbital that it occupies. Electrons are lowest in energy when they occupy a 1s orbital because the 1s orbital is closest to the nucleus and it has no nodes. The more nodes that an orbital has, the greater its energy. The 2s orbital has one node and is farther away from the nucleus. It is therefore higher in energy than the 1s orbital. After the 2s orbital, there are three 2p orbitals that are all equivalent in energy to one another. Orbitals with the same energy level are called degenerate orbitals. As we move across the periodic table, starting with hydrogen, each element has one more electron than the element before it. The order in which the orbitals are filled by electrons is determined by just three simple principles. 1. The Aufbau principle. The lowest energy orbital is filled first. 2. The Pauli exclusion principle. Each orbital can accommodate a maximum of 2 electrons that have opposite spin. To understand what spin means, we can imagine an electron spinning in space, although this is an oversimplified explanation of the term spin. Electrons have 2 possible spin states, designated by arrow up or down. In order for the orbital to accommodate 2 electrons, the electrons must have opposite spin states. 3. Hund's rule. When dealing with degenerate orbitals, such as p orbitals, 1 electron is placed in each degenerate orbital first, before electrons are paired up. The application of the first 2 principles can be seen in the electron configurations of hydrogen, helium, lithium, and beryllium. Additionally, the application of the 3rd principle can be seen in the electron configurations for the remaining second-row elements: boron, carbon, nitrogen, oxygen, fluorine, neon. Thank you for watching. Click subscribe to support this channel.